Hello everyone and welcome back. Today we're going to talk about vectors. So let's begin by the very simple definition, shorthand definition of a vector. Simply put, a vector is a directed line segment. The fact that we use the word directed implies that there's a direction associated with every vector. And the fact that it is a line segment, it implies that there is a magnitude to every vector. So every vector has a magnitude and direction. Now, how are we going to represent a vector? So suppose this is a directed line segment. So to have a line segment, I need to have 2 points. And there you go. So the line segment is actually the distance from P to Q. That would be the line segment. And usually for line segments, we use the letters that represent the initial point and the terminal point of that line segment, and we put just a bar on top of that. This indicates that I have a portion or a segment of a line. Okay, now P here, we're going to call P the initial point, and Q here is going to be the terminal point. And if we put an arrow on this line segment, now we have a directed line segment again, which is what PQ is. So I have initial point of a vector and I have the terminal point of a vector now. The notation for writing a vector, generic letter V for vector, and this is actually an arrow above that, so that means vector V, which will be the same as the line segment PQ with an arrow on top, which turns it into a vector quantity. Now, a lot of textbooks use bold-facing, so they can also write it this way. They use boldface V in this case. Now, for me, it's going to be difficult to boldface everything as I go, so I'm just going to go and opt into that first notation. I'm going to use the name of the vector, A, B, C, D, whatever it is, in this case V, and an arrow above that. Okay, now the zero vector, since we talk about the magnitude, what is a zero vector? Well, a zero vector is one that has a magnitude 0, right? Just going to say magnitude is equal to 0. And because magnitude is 0, the direction doesn't matter. It could be any direction. Okay, any direction. Now, indirectly, we don't really, because it has a magnitude 0, so we don't use it itself per se directly, but sometimes the sum of vectors could equal to a 0 vector. Two vectors are equal. I'm talking about equality of vectors now. So what are equal vectors? Well, equal vectors are those that have same magnitude and direction. So let's say I have vector V equal to vector W. In order for these two vectors should have the same magnitude, let me write that, and they have to have same magnitude and same direction. Both of those must be in place, both very important. Same magnitude, same direction. So for instance, let's say I have a vector V like this, and I have a vector W elsewhere like that. These two vectors must be going exactly in the same direction. Okay, even the same angle of elevation or depression in this case, and they must have the same magnitude. So if the magnitude of this vector, let's say, is 5, so is the magnitude of this vector. In other words, they're a carbon copy of each other, except they're allowed to be located elsewhere on the plane. They don't have to be on the same, They don't have to go from same start, initial point, same terminal point at the same location. They could be located elsewhere on the plane. When it comes to properties of vectors, well, there are a lot of interesting properties with vectors that works almost with like real numbers. So for instance, vector addition. Vector addition is commutative. Okay, the addition of two vectors is commutative. So it doesn't matter how you add them, v plus w, w plus v. Now when we look at the associative property, so let's say I have u plus the sum of v and w. Okay, we can actually combine u and v together and then add those to w. The associative property allows us to change the grouping, how we group the vectors together. We already talked about the zero vector, so the property, addition property with zero vector. Any vector added to zero vector in any order will give you the vector itself. Okay, and any vector added with its opposite, that's negative of v, gives you the zero vector. Okay, so what does the opposite of a vector v looks like? Let's say if this is vector v, going in that direction, well, vector negative v will go same magnitude, but it goes in the opposite direction. Okay, and then we can talk about the difference of vectors. Now, because subtraction is not commutative, by the way, it makes a difference whether you do v minus w or w minus v. But let's say I want to subtract two vectors, this case w from v. Well, we change it to addition with opposite. And there you have it. So in other words, to subtract vector w from v, we add opposite of vector w to v to make that subtraction. Now, how do we add vectors? So let's talk about vector addition. There are a couple of ways we can do this, the vector addition, that is. One is the triangular method. So for this method, suppose I have vector v here, okay, and I have vector w here, and I want to add these two. So here's how we can do this. We can write vector v and vector w. I'm going to actually move it from where it was, from here, literally move it to here, right? Because that's not going to change the magnitude nor direction of w. Okay, and this is often called tip to tail method. Tip to tail method. Okay, that is the tip of this vector is connected to the tail of w. So we have the tip to tail method. Now, what does the sum vector look like at this point? I can close this figure and there you have it. It forms a triangle, right? The sum forms a triangle here. And there you have it. That would be the sum vector of v plus w. Triangular method. Or we can use the parallelogram method. So parallelogram method, suppose this is vector v, vector w. I'm going to actually draw it here. And then I can form a parallelogram this way. This vector w, I'm drawing an equivalent vector w on the other side, and the vector v would be the other side of that parallelogram. Now we have created a parallelogram, and like in a triangular form, the diagonal is going to be the sum vector. So if I draw things to scale, it will be exactly the same. This one is kind of like a tail to tip method, if you want to call it. It's the tail of one, tip of the other, that connects together. Okay, so that's how we add vectors geometrically, that is. A lot of times we do this algebraically without even drawing the vectors. So let's take a look at an example here. Suppose I want to find two vectors. One is the difference v minus w, and another separately w minus v. Okay, and what do v and w look like? Well, suppose that this is vector W, and this one is vector V. All right, and we want to do V minus W. So in order to do V minus W, this is W. So I'm going to do a V minus W. Yep. So this is V, and that's vector V. We're going to do negative of W. So negative of W actually goes in the opposite direction, correct? Same magnitude, but goes in this direction, not in the other direction. Right? So this is now negative W, and we're going to add those together. So how do we add them together? Again, we're going to go tail to tip, and this is going to be the difference vector. This is V minus W. And then I can translate this vector to the original right there. That's going to be V minus W. Okay. So we can kind of make an interesting observation, by the way, here. When we have vectors that are situated like I have here, two vectors that emanate from a common point. To find V minus W, you actually go from tip of W to tip of V, and that will give you V minus W. Okay. Now let's do W minus V. Let's do W minus V. And this is the answer to V minus W. If I want to do W minus V, so this time, this is W, and remember this was V. I'm going to do negative of V. Well, negative of V will go in this direction, but it will have the same magnitude, correct? That's negative. And then using the same tail to tip method, I can draw right in here from the tail to the tip of the vector using a triangular method. And that's going to be the vector, in this case W minus V. Make sure you put the vector, by the way, on top of the letter. If you write W minus V, that is incorrect, and nobody likes, that notation. Okay, so here's W minus V. So if I go in terms of the original configuration I had now, remember, let's say this was W and this was V. To do vector W minus V, you actually go from V to W, from the tip of V to the tip of W, and that's W minus V. Okay, and there you have it. Simple, but again, just have to be careful and pay attention a little bit to the detail here. So that's how you add or subtract vectors together. Okay, now let's take a look at scalars now. The next idea we're going to talk about. Let's talk about scalars. Now, in the world of vector manipulation, scalars are real numbers. With respect to vectors, they're called real numbers, or simply scalars. Now, scalars have only magnitude. Remember that. There's no direction. It's like number 2. That's it. It's not a vector quantity 2. So it's just a magnitude. There's no direction. So for example, quantities that would be scalars in real world. Time, for example, is a scalar. Right? Temperature doesn't have a direction. Time doesn't have a direction. Speed doesn't have a direction. It's how fast you go. 70 miles an hour. There you go. There's no direction. You're not going north, east, south, or west. Mass would be another. So let me just write these. Example of what you call it scalars would be mass, volume, for example. Things like that. These are all scalars. Things that don't have direction associated with them. Time, and let's throw in temperature, area, things like that. These are all magnitudes. Okay. Now, when we talk about the scalar multiple of a vector, scalar multiple means a real number times a vector. And that's we're going to use, like your textbook uses, use alpha. It doesn't matter. Some use A, B, C like that. So I'm just going to use alpha times V. Notice alpha is just a scale, a magnitude. Now, the case where alpha is positive. If alpha is positive, then alpha times V, the scalar multiple, will have same direction as vector V. Okay, but the magnitude is alpha times the magnitude of V. Okay, so in other words, this vector V has a magnitude of 2, alpha is 3, then alpha V has a magnitude of 2 by 3, which is 6. And in the case where alpha is negative, the negative scalar actually causes the vector to go in the opposite direction. So alpha V will have an opposite direction. Opposite direction as V. Okay. And it will have, again, the magnitude that is alpha times magnitude of V, absolute value of alpha this time because it's negative. Okay, now let's take a look at some properties of scalar multiplication. The properties of a scalar multiplication. The zero scalar times vector V gives you the zero vector. Notice, so we got to be careful. We have two kind of zeros in vector field. Okay, or the field of vectors. Zero is a scalar, and we have a zero as a vector. See the difference between them? So what do they look like on the number line, let's say? Oops, I better be careful. Don't put any signs. There you go. That's a zero scalar. A zero vector looks like this, and it has just an arrow. And the arrow could point in any direction. There you go. Could be in any direction. It doesn't matter. Okay. There. Whatever. So just want to point out that there is a difference between a zero scalar and a zero vector. Now, scalar 1 times any vector gives you the vector itself. And negative 1 times vector V gives you negative V. And that's why when we subtract, when we do like W minus V, it's like W plus negative 1 times V. Okay, the other facts of scalar multiplication for general alpha and beta, let's say, if I have two scalars now, alpha beta multiplied by V, then we can write it as alpha V plus beta V. Alpha times the sum of two vectors. You multiply the scalar by each vector. This case will be alpha W. Okay, and if we go alpha times beta, and let's do it this way. Let me change that. I want to go alpha times, let me make it like this, beta V. This is better. I can multiply the scalars together and then that times the product. So for example, if I have 2 times 1/2 V, it'd be easier for me to do 2 times 1/2 and make a whole, and then just go with vector V. Okay, now let's talk about the magnitude of a vector. So when we're talking about the magnitude of vector V in this case, how do we write it? The magnitude of the vector, we use double vertical lines. There you go. It looks like double absolute value lines. And that means the magnitude of V. Now, some of the information about the magnitude of every vector is positive. 0 is the lowest it can be. The magnitude of the vector is 0 only for a 0 vector. See that? IFF means if and only if the vector is a 0 vector. The magnitude of a negative vector is the same as magnitude of a positive vector. And the magnitude of a scalar multiple of a vector is equal to absolute value of the magnitude of the vector, absolute value of the scalar, times the magnitude of the vector. For example, here, real quick with this one, let's say I want to find the magnitude of negative 2v. See, if I just say that's negative 2 magnitude of v, now that implies the magnitude of that vector is negative, which defies what we said earlier right in here. We said magnitude has to be positive. So it's for that reason we take absolute value of negative 2. So the magnitude of this vector is going to be twice magnitude of the original vector v. Okay. All right, and then let's talk about unit vectors. A unit meaning 1. A unit vector, in fact, is a vector whose magnitude called u the vector. It's a vector whose magnitude is 1. So let's say this is 1 unit, what I have. That's a unit vector. If this is 1 unit, this is a unit vector. That's 1 unit. That's a unit vector. 1, 1, 1. Every one of those have magnitude of 1. They can point in any direction. Okay. Next, talk about the algebraic vector. Okay, an algebraic vector. What is an algebraic vector? V. Algebraic vectors are indicated using their components A and B, where A and B here are scalars. Okay, A, B are scalars, and we call these components of vector V. That's what that is. Okay, now having talked about algebraic vector, we can talk about a position vector. Position vector play a key role in physical sciences and engineering. So what is a position vector? Well, the idea of position vector is this. Suppose I have, here's my coordinate system, x, y. Let's say I have a vector that's over here. You see that? How it's away from 0, 0, somewhere on the plane. If I have a position vector, it means I have exact same vector drawn to where the initial point starts at 0, 0. You see that? Call it vector v. This is vector v. So that's what the position vector is. It's, again, a position vector is a vector whose initial point is at the origin. Let me just write that. Initial point at the origin. The terminal point could be anywhere, but it has to initiate from 0, 0. Okay, from the origin. And this is point, let's say AB, where this is A and there is B. You see how that works? Okay, now for any vector V, let's say that has initial points that are not, that they don't initiate from 0, 0. So let me write this first. For any vector V with, let's say my initial point is going to be at some point, let's say x1, y1, and P2 is the terminal point of the vector at x2, y2. Let me say, so that the vector V can be formed as P1 to P2 with an arrow on it. We can define another vector W that's equal to V. That means it has the same direction and the same magnitude, except it's located elsewhere. Vector W, so that W is x2 minus x1, y2 minus y1, is a position vector. So what I'm saying here is that every vector could be turned into a position vector to where it starts at 0, 0. could be anywhere on the plane. You can grab it and put the initial point at 0, 0 and let the terminal point be wherever it wants to be. Okay, so that's what this is. Every vector could be written as a position vector. Now let's talk about the vector equality. Okay, the vector equality. For vector equality, suppose I have two vectors now. I'm writing the algebraic form of V is AB and W is algebraic form CD using angle brackets. These two vectors can be equal together if and only if they have exact same components. A should be equal to C and B should be equal to D. Okay, and that's what the vector equality is. And then we're going to talk about the famous, all-important, the IJ vectors. And by the way, everything we're doing in this section is in 2-dimension. There's a 3-dimensional version of the vectors which you deal with in your multivariate calculus. So the IJ vectors are on plane, and there is a k vector in a 3-dimension, but in 2-dimension, vector I, what does vector I look like? As components, it has 1, 0. I and j, by the way, are unit vectors. I, j are unit vectors, meaning they have a magnitude of 1. So I is in the x direction. And what is j? Well, j vector is 0, 1, going in the y direction. Okay, and these are unit vectors. So let's say here's x and there is y. What does I look like? Here's I and here's j. There's I and that's j. Remember, makes a difference. Don't call the vertical one I, because its components are 0, 1, not 1, 0. They have to look like that. There's only one I and there's only one j. Okay, and they look exactly like that. Now, having drawn this the way I have, you can see that the two vectors are what we call perpendicular, or in vector lingo, vector terminology, they're called orthogonal vectors. Now, having defined ij, let's talk about the I hyphen, it's not I minus j, ij form of vector v. Every vector could be written in algebraic form, which is the component form, right? AB. And it also can be written as AI plus BJ using those unit vectors. And this is commonly called the IJ form. IJ form. Engineers tend to use this form quite often. Okay. And so what does this look like? You can see the proof of this, by the way. You can, I is vector 1, 0. J is vector 0, 1. A and B are scalars, right? So you can multiply A times 1, 0. You get A0 plus 0B. And when we add vectors, you add like components, the x's and the y's, so to speak. And there you go. See that? So for example, let's say I want to write vector 2, negative 4 in ij form. So that's going to be 2i, negative 4j. Again, it's very important, folks. I and j, these are not unit vectors unless you put the arrow on top. Without them, they're scalars. Now, let's look at the addition and subtraction in algebraic form. Addition and subtraction in algebraic form. So let's say I have a vector v. Vector v in components form is ai plus bj, b1j. And the second one, vector w, is going to be a2, again I, plus b2j. So each has its own components. And I'm going to let scalar be alpha. So when we do v plus w, that's when you do a1 plus a2 in the I direction, and then you combine b's in the j direction. In component form, you can write it as a1 plus a2, b1 plus b2. This is personally my favorite form, the last one. The ij takes sometimes a little longer to write when you have too many manipulations. The difference, a v minus w is going to be a1 minus a2 in the I direction, and then you subtract b's in the j direction, and that will make it a1 minus a2, b1 minus b2. See that? What if I have a scalar multiple, alpha times vector v in the ij form? You do scalar times a1 I, and you do the scalar times b1 j. In components form, you have a alpha 1, and you have, let's say I'm doing a1 b1, yeah, and I have alpha or b alpha. However, they're both scalars, so it doesn't matter. I'm going to go alpha a1, alpha b1. How's that? We put alpha outside of each of those. Now the magnitude of the vector, by the way, now that we have the components, is when you do a1 squared plus b1 squared, take the square root of. Magnitude of w is going to be a2 squared plus b2 squared. It's just like any two vectors. You add it's sum of the squares of the components, take the square root of. And what does the vector look like on a plane? Let's say this is vector v, whose components are ab. This would be a, and this would be b. In this case, I'm going a1, b1, just to keep it consistent. And that's what this is. Okay. Now, let's take a look at another idea, having talked about all of these. And this time, sometimes we are interested in having a unit vector in the same direction as v. So for example, let's say this is vector v, and I want a unit vector, means length 1. There you go. Call it u for the unit vector in the same direction. And why do we want to do this is maybe let's say vector v is magnitude 5, so I can write it in terms of 5 unit vectors. So let me write this. What we want to do is we would like to find a unit vector in the direction of v, vector v, another vector, a second vector. So this would be my first, well, let's call v the first vector, and this is the unit vector, the second vector in the direction of v. Now if I throw in the coordinate system here on top of this, so let's say this would be the angle theta that the vector makes with the horizontal. Okay, now the unit vector is going to be given, it is given by 1 over the magnitude of vector v times vector v itself. Remember, this is a scalar, because magnitude of v is a scalar, 1 over v is a scalar. 1 over magnitude of v is a scalar. And you multiply it by v. Now, because magnitude of v is positive here, right? This means u has the same direction. Okay, it's going to have the same direction as v. In other words, because you multiply them by a positive scalar, so it will have the same direction. Now the proof of this one, just to show you that it is a unit vector, if I call vector v using its components, let's say a, b, right, then the magnitude of vector v from before, we know that's a square root of the sum of the square of the components of it, right? Now vector u, which is v over magnitude of v, that's just another way of writing what I have up here. And this is given by, in the ij form, that's ai plus bj over the magnitude is the square root of a squared plus b squared, right? So we can write this in components form as a over the square root of a squared plus b squared and b over the square root of a squared plus b squared. Okay, and that's what the unit vector u is going to look like. Now, just to show you that magnitude of u is actually 1, that's when we take the square root of the square of its components, right? So I'm going to square each of those. That means a over square root of a squared plus b squared plus b over the square root of a squared plus b squared. All right, and we can combine the radicand. We have LCD, which is a squared plus b squared. And I forgot to square it. Ooh, big mistake here, right? Because it's sum of squares of the components. That's why it wasn't looking good. There. So when you square each of these, they have the same denominator. We're going to lose the radical. Then we have simply a squared plus b squared from the first and the second fraction, right? And the radicand is the same, so you get square root of 1, right? The radicand here, the numerator and denominators are the same, so you get the square root of 1, and that's just 1. Okay, so it is in fact a unit vector, the resulting vector. Now, one consequence of this is that we can write any vector v as magnitude of v times a unit vector, right? Provided the u has the same direction as v. Okay, and that comes again directly from this relationship. Because magnitude of v is a scalar, so multiply both sides by magnitude of v, and this is what we get. All right. Now, let's talk about direction angles here. Okay, a direction angle is just that. It's the angle that's associated with a vector in the direction of the vector. So suppose I have, this is a vector, vector v. There you go. Let's say I have this vector v, and this is the direction angle theta. Okay, and we can decompose this into its components, right? We have a horizontal component of the vector, and we have a vertical component of that vector. The direction angle is angle theta in this case. Okay, that's what the direction angle is. And we can, if we make this, let's see how we're going to do this. Let me do this for a unit vector. Let's say I have a unit vector. Okay. And because this is a unit vector, I can make it like this. So the coordinates of this point is 1, 0. Coordinate of this other point is 0, 1. And here's my unit vector, which sits at an angle theta here. This is what u is. Okay. Now, we can tie this in with the unit circle from earlier, and we say that the components the coordinates of the terminal point of that unit vector are going to be cosine theta, sine theta. What we're trying to do is we're trying to connect this with sine and cosine. Okay. Now, because u is a unit vector, therefore 1, 0 here, we can think of this in terms of the I vector, I and j vectors, right? So let's say here is a vector in the horizontal direction, and this is a unit vector component of it in the vertical direction of that unit vector. All right, so now we have two components of that unit vector. Magnitude of u is 1 because it's a unit vector, and the vector itself, u, can be written as cosine theta I plus sine theta j. Remember, this is in the ai plus bj form. Okay, and the components are ab of that unit vector. All right, now if I have a vector v, let me go back to this one. If I have a vector v, let's say this is one that's clearly not a unit vector now. Okay, but I can actually create a unit vector in that direction. Let's say this is now a unit vector. Let me go higher. Call this a unit vector in the direction of v. And we can actually decompose this into vector v into horizontal vertical components. And there you have it. This would be a horizontal component of v. This would be the vertical component of v, just like I had before. The difference now, I managed to fit in a unit vector on that. All right. So I can write vector v as magnitude of the vector times the unit vector. Remember this relationship? I'm writing it here now. The unit vector, we just said I can write it as cosine theta times I plus sine theta j. And remember, don't multiply these. Theta times I. Okay, this is what it looks like. And I can further combine magnitude of v times cosine theta. This would be in the I direction, plus magnitude of v times sine theta in the j direction. All right, and this would be, again, the horizontal component of the vector plus the vertical component of the vector. And this will enable us to, again, break down or decompose any vector into horizontal, vertical components. Okay, so for example, let's say I have a vector that goes like this. Suppose, there you go. This is vector v whose magnitude is, let's say, 10. Okay, and this is the horizontal axis, this is the vertical axis, y. The vertical component of that vector is right here, this one. Right, this is vector v vertical component, and this will be the horizontal component, v horizontal. Okay, and for this specific example I have, this, let's say this is 6j, and this would be 8i. And there you have it. So I can break it into two components. So that's the idea of what we have up here. Okay? And there you have it. So I'm going to finish this video, so it won't be too long. So I'm just going to make this a lecture on vectors, some basic principles, definitions, operation with vectors. Then I'm going to do another video separately where I'm just going to have examples of vectors, so it doesn't make the video too long. Okay, so I'm done with this, again, with this lecture, and then another lecture I'm going to start right away where I do some examples for you. Okay, thank you for watching.